here we deal with the rotational motion and the rolling motion of a cylinder that's shown here. So we want to find out what its kinetic energy is. Okay, so we will do this in a couple of different ways. What we'll do is that we'll put our reference frame here and compute the kinetic energy. And to show that the kinetic energy is independent of the reference frame, we will put another reference frame here and we'll find the kinetic energy with respect to that. Okay, so we'll do it two ways. So here is a cylinder, as I mentioned before, it has a radius r. It's rotating this way, therefore it's going to roll towards the right. With the velocity of the center of mass is VCOM. Okay, so let's look at these 3 points: the point of contact, the center of mass, as well as the very top. Okay, so if you see here, the linear velocity at C, is the velocity of the center of mass, and that's just VCOM, right? Now, if you look at this position, the very top, linear velocity at T equals V center of mass plus the velocity imparted by rotational motion, okay, that is r times omega. And here we will use a capital R because that's what we have this in the diagram. Now the thing is that the cylinder is undergoing rolling motion, so under those circumstances, and especially when there is no slipping at all here, we have that V center of mass equals r omega, right? So essentially this becomes 2 times V center of mass, okay, and that's the linear velocity at T. So if we look at the point P that's at the point of contact, we see here the linear velocity at point P equals V center of mass, and we realize that this point has a component due to rotational motion that is moving in the opposite direction. Okay, so we have minus r times omega, and since V center of mass is equal to r times omega, this is 0. So essentially what happens here is that this point of contact is momentarily at rest, okay, and every time there is a different point that comes into contact, a different point on the cylinder comes into contact with the floor, okay, but momentarily at the point of contact, the velocity, the linear velocity, is actually 0. Okay, so if we look at the reference frame, at point C, so we place our reference frame here and we want to find out our total kinetic energy. The total kinetic energy here equals half mv center of mass square, that is the kinetic energy of, this is the kinetic energy of linear motion. To that we add the kinetic energy of rotation, it is half I omega square. And here the I is the moment of inertia at the center of mass. And we know that for a cylinder, the I center of mass equals equals half m times r squared. We know that, right? So this expression can be written as half m v center of mass square plus half times half m r square omega square, right? And r square omega square, this is nothing but v center of mass square. So let's do that. Let's write it that way. Half m v center of mass square plus 1/4 m v center of mass square. So that becomes equal to 3/4 m v center of mass square. Okay, so that's what we get. So that is the total kinetic energy of the rolling cylinder. You know, the cylinder is rolling about its axis, its long axis, and the reference frame here is at point C. That's the center of mass. So now let's do this. Change the reference frame to point P. Now let's place our reference frame at point P. So here if we see here, the entire cylinder rotates as a rigid body, okay, around the point of contact, right? So essentially this rotates like that, this rotates like that, and that happens at that particular instant. So the omega here, okay, if you want to find out the angular velocity at point C, right? So it is nothing but the velocity of center of mass divided by the distance from the axis of rotation. In this case it is r, and that is equal to the omega that we have seen earlier, right? So that is equal to the omega that we have seen earlier, because the v center of mass equal to r times omega. So if we look at the omega at point C, at point T rather, so here it's the velocity at point T divided by the distance from the axis of rotation, that is 2r. Okay, this is 2 times v center of mass divided by 2r. The 2's cancel out and we get back omega. Okay, so we see that to be true. So here the kinetic energy, okay, here has a zero translational component, because there is no explicit linear velocity here, right? There is no explicit linear velocity about this frame of reference. Now to add to that, we have the rotational kinetic energy, which is I at point P, okay, half times I, that's moment of inertia at point P, times omega square. So by the parallel axis theorem, I at point P equals half m times r square plus m r square, okay? Because what we have done is we have moved the axis of rotation from here to here, and this distance is r, and that is nothing but 3/2 m r squared, right? So we plug this value here, right? We plug this value here and we get the kinetic energy equals half times 3 divided by 2 m r square omega square, okay? And this is nothing but center of mass square. So we get here, the expression we get here is 3/4 m v center of mass square. So what we see here is that the kinetic energy rather it's the expression for kinetic energy or its value is independent of the frame of reference. Okay, so we needn't worry about the frame of reference that we we are using for our computations. Okay, so that's a very important result of the uh, rotational physics. Now let's look at a slightly different problem. Okay, so here we have the same cylinder. We have the same cylinder that's rotating and rolling. Okay, so we have a rolling cylinder here too, but the cylinder here, for the purposes of argument, okay, is looks like a spindle. Okay, and we assume that these masses are actually quite negligible, and the arms of the spindle have almost zero radius, and they are being pulled along by a string with a force F. Okay, so that's the thing, and so we want to find out what is the maximum force that we could apply. Okay, what is the maximum force that we could apply before the cylinder starts to slip. Okay, so that's the important factor. Now there are a few things to consider even before we do this. So people may ask this question, right? So now the thing is, how is this rolling at all? So what happens is that the force that's being applied goes through the center of mass, so it has no torque. The weight of the cylinder goes through the center of mass, acts downwards, and it has no torque. So the normal force acts upwards through the center of mass, and it also has no torque. The only thing that has torque is the frictional force. Okay, so the torque exerted by the frictional force is frictional force times the radius r. So the question also will come to mind is, why is the friction force not doing any work? Okay, it's not doing any work. So there is at the moment there is no dissipation. Okay, so there is no dissipation, and so the reason is because this point here is at rest. This point P is at rest. Therefore, although there is a torque, it doesn't do any work. Okay, so that's the important part. Okay. So now, for the purposes of linear motion, we will consider the cylinder to be a point. Okay? We'll consider the cylinder to be a point, and so the force towards the right is the applied force, and the force that's resisting motion is the frictional force. Okay, is the frictional force. So now, the net force towards the right is the frictional force is the applied force minus the frictional force equals mass times acceleration. So that's the expression for the net force and how that relates to the acceleration. Right? Now we know that the frictional force times r is the torque, and that should equal to I times alpha, and alpha here, right? Alpha here is nothing but the acceleration of the center of mass divided by r, right? So that's what it is. So therefore the frictional force here equals I times a, right, divided by r squared. Okay? So what we do here, okay, is find the expression for A, in fact, because we are interested in knowing the relationship between the applied force and the frictional force. So let's do it that way. So A here equals frictional force times r squared divided by I. Okay, so that's what happens. So now we plug this value of A here, plug this value of A all the way here, and so we have F minus the frictional force equals frictional force times r squared divided by I. Okay, or we have the applied force equals frictional force, okay, times 1 plus m, and this has to be multiplied by m here, m times r squared divided by I. So, so the thing here is that, so what is the maximum value of the frictional force? The maximum value of the frictional force is actually mu times m times g, right? And the frictional force cannot exceed that, okay? So that's the interesting part. So now, so the maximum force, okay, is essentially mu times mg times 1 plus mr squared divided by I. Okay, so the maximum force that can be applied to this cylinder, okay, in this particular way, that you're dragging it, okay, by applying a force essentially at the center, okay, it cannot exceed this particular expression on the right. Okay, now if you have a proper cylinder, I equals mr squared divided by 2, right? So the F max mu mg 1 plus mr squared, or the mr square divided by 2, and here these cancel out. So F max equals 2 mu, actually it is mu mg 1 plus 2, so it is 3 times mu mg. Okay, so that's what we get. So the maximum force that we can apply, okay, before this cylinder starts to slip, okay, essentially cannot exceed 3 times mu mg. Okay, so bear in mind that these are computations done under ideal conditions. Okay, real life situations obviously will change. Okay, so but we have captured the essential physics of the problem. Okay, and we have understood, right, that you can always apply a force that exceeds the force of friction, and this will cause the cylinder to slide. Okay, so and then before that we have looked into finding the kinetic energy, okay, and assuring ourselves that the kinetic energy is independent of the frame of reference. Okay, so right, so I hope the two problems together give us a flavor for rolling motion and rotational dynamics. If you like this video, please press the like button and subscribe to this channel. Thank you.